this next example, we're going to go to something a little bit more familiar, maybe a bit less abstract. We want to find the fifth degree Maclaurin polynomial for the sine of x. Well, that's something we have memorized, right? The sine of x function can be approximated using the Taylor polynomial expansion that when we did all the derivatives, we saw that it worked out to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. Now I'll stop there because it says the fifth degree. Okay, so it says then use your polynomial to approximate sine of 1. So let's see, the sine of 1 is pretty close to 0, right? C equals 0 here. So 1 is pretty close to 0, so we would expect this to be a decent approximation. So sine of 1 is approximately equal to, I'm just going to replace every single x with a 1. So we've got 1 minus 1 cubed over 3 factorial plus 1 to the fifth over 5 factorial. All right, now I worked this out a little while ago and I found that 3 decimal places wasn't really enough, so I'm going to say 6 because we're going to find that these errors are so incredibly tiny. Okay, so when we work out the decimal approximation here, we get, let's see, what do I have here? I got 0.841667. That is an approximation. It's a rational approximation. We could get it as a common denominator if we felt like it, but this is a rational approximation of the irrational value sine of 1. All right, and then it says use Taylor's theorem to find the maximum error of your approximation. So in other words, find r, right? Or not find r, we can't find r, but find the largest possible value of r. Now here's a question, r sub what? You might say r sub 5, and you wouldn't be wrong, but we could do better than that. I'm going to call this r sub 6, and I'm wondering if anyone can understand why. I think we might know from the pattern what the degree 6 term is going to be here, right? The degree 6 term is going to have a 0 coefficient. So t sub 5 of 1 and t sub 6 of 1 are both going to be 100% exactly the same thing because there is no degree 6 term in the expansion of sine of x. So I'm going to go ahead and go to the highest possible n value just so I can get the best idea as to the accuracy of my approximation. Again, if you used r sub 5, I could not count off for that. However, it's better to use r sub 6. All right, so we're going to find r sub 6 evaluated at the x value that we're talking about, which is 1. And according to the Lagrange error bound, we know that this is going to equal the next derivative of the function evaluated at some value z having to be between x and c. In this case, c equals 0 and x equals 1. And then n plus 1 factorial, or 7 factorial. And then x minus c. Let's see, x again is 1 and c is 0. So we're going to raise 1 minus 0 to the 7th power. That's nice. All right. So what is the 7th derivative of sine of x evaluated at z? Well, I don't know. You don't know either, because we don't know what z is. But we do know, based on the fact that f of x is sine of x, we know that f of x and all its derivatives, f of x and all its derivatives output values strictly between the interval -1 to 1. Okay, so sine of x, cosine of x, negative sine of x, negative cosine of x, those are the only derivatives we're talking about here, folks. And all of those functions always return values between 1 and -1. So if we're going to find the maximum value, remember we're not going to figure out what the actual value is because we can't. But if we want to find the maximum value, just let that value equal to 1. And when I say that value, I'm talking about this value right here. The maximum value equals 1. Okay. I don't know what it's going to be, but there's no way it can be bigger than 1. So I'm going to say that this guy right here, this error, for sure, guaranteed, is definitely less than or maybe equal to, probably not. I'm going to just replace that messy numerator with a 1 over 7 factorial times 1 to the 7th. Okay, well, what is 1 divided by 1 to the, not the 7th, 7 factorial? Well, that's when I got into the, well, 3 decimal places isn't enough, because if we go to 3 decimal places, we get 0.000, and that's not a very interesting error. So if we go to 3 more decimal places, we get 198, okay? Really, really teeny tiny error here. Okay, so that is the maximum error for the approximation. In other words, this guy right here is really, really close to sine of 1. Okay, so how can we find those a and b values? Well, let's see. The a value, a, is going to be equal to the Taylor polynomial approximation. I'll call it t sub 6, I guess, minus r sub 6 of 1. I could call it t sub 5, I guess, but since I'm using r sub 6, I'm going to use t sub 6 as well. And b is going to be equal to the approximation plus the error, right? So when I work those guys out, I see that the interval in which sine of 1 must reside is, when I subtract, I get a equals 0.84149, and when I add, I get b equals 0.841865. Okay, and those guys match. Let's make that a little bit more legible, maybe. It's always good to be able to read what you've written. 84149. All right. So those two numbers are really, really close to each other. So let's take a look. Could sine of 1 equal 0.9? Well, no, because 0.9 is not an element of that interval a to b, right? It's bigger than the maximum. 0.9 is too big. It's bigger than the maximum which was t sub 6 of 1 plus r sub 6 of 1. In other words, 0.9 is greater than 0.841865. So I can't resist this. I want to actually use my calculator, since obviously I've been using my calculator for all of these problems. I guess both of these problems at this point. There are only 2. What does the calculator say the sine of 1 equals? And when you type that in, you see that the sine of 1 is actually, I'm going to go and say equals to, even though I'm rounding, because it's easier, basically. 841.841, whoops, put another point there, distracted myself, 0.84147.1. All right, let's see, is that actually in the interval? Let's see, this is 841, so those match, and then 471, oh, this matches to 4 decimal places, but then this 7, aha, the 7 right here is not the same as the 6. In fact, that 7 is bigger than that 6. My goodness. Sine of 1 is just barely bigger than that lower bound. So, but it is bigger, right? So we have, in fact, shown, using a calculator, that t sub 6 of 1 minus the error, r sub 6 of 1, is definitely a good lower bound for the sine of 1. Okay, clearly it's bigger, or clearly sine of 1 is smaller than the maximum, because it's not quite as close. Those don't even match to 4 decimal places. But yeah, this is definitely, the calculator does support Lagrange error bound, which is always nice to have some validity to your result. All right.